Hey guys, my name is IBM and I'm still taking you through waves and superposition. I think this is going to be lesson 10. I think this is going to be lesson 10. And in lesson 10, I'll basically do examples under stationary waves, especially with pipes, examples under stationary waves. And I'll also introduce diffraction, remind you of the concepts of diffraction that you mentioned in IGCSE. And I think that will be the end of lesson 10. So we are going to finish with stationary waves and then we go to diffraction in lesson 10. So let's go. Okay, so we are finishing up with the stationary waves and we shall introduce diffraction. That is in this lesson 10. So basically in lesson 9, I think in lesson 9 we saw stationary waves in pipes or formation of stationary waves in pipes. We saw how to determine the frequency, how to determine the wavelength of stationary waves for microwaves. We also saw how to measure the speed using stationary waves. And so I just want us to do examples with these or calculations in standing waves or stationary waves, either on strings or on pipes. Examples. Question number 1. So if a violin string vibrates, so it is a string. It is a string. It vibrates with this frequency as its fundamental. So this is F naught. What are the frequencies of the first 4 harmonics? Remember, for a string, Fn is equal to n times F naught, where n equals to 1, 2, 3, 4, and so on and so forth. So for the first one, the question is, what are the frequencies of the first 4 harmonics? So the first harmonic is the fundamental mode of vibration, which is F1, and F1 is equal to 1 times F naught. So the first one is just going to be 440. The second one will be F2, which is going to be twice F naught. The third one is going to be F3, which is 3 times F naught. And the fourth one is going to be F4, which is going to be 4 times F naught. So this gives us these frequencies are 440, 880, 1320 Hertz, and 1760. So those are going to be the frequencies. A violin string vibrates at 294 Hertz when unfingered. So this is going to be the fundamental mode of vibration. At what frequency will it vibrate if it is fingered 1/3 of the way down from the end? So if it is fingered 1/3 of the way down from the end, it means the length L which remains is going to be 3 over, let me see, 1 minus 1/3, I think it becomes 2 over 3. The length which remains is 2/3 of a wavelength. So if it is unfingered, we shall have the fundamental, which is given by V over wavelength. And for the fundamental mode of vibration, wavelength L is equal to, I can sketch this here. For the fundamental mode of vibration, we have something like this. And L equals to half of wavelength. So the wavelength is equal to twice L. So this becomes V over 2L. So it means 294 is going to be V, which V is which V, I'll just leave it here. At what frequency will it vibrate if it is unfingered? So I'll just say V over 2L, that is one equation. Then if it is fingered 1/3, it means L is going to be 2 over 3 wavelength. So it means in that case, F, when it is fingered, is going to be equal to V over the, here lambda is going to be 3L over 2. So this becomes 3 sorry If it is fingered 1/3 of the way down the end, it means the new length L is going to be 2/3 of the original length L. So the new length is 2/3 of the original length L. So it means the new frequency is going to be V over wavelength, or V over 2 into the new length, which is going to be 2 over 3 times L. So it means F is going to be equal to 3 over 3 over 2 into V over 2L. And of course, V over 2L is 294. So it means F is going to be 3 over 2 into 294. And I think this gives us the frequency we are talking about here. This is a more advanced equation. So 3 divided by 2 times 294. So this will be 441. Okay, so when it is unfingered, this is what we had. When it is fingered, the new value for L is 2 over 3 because it is fingered 1/3 of the way down from the end. So that means the length which remains after the third is removed is 2 over 3 of the original length L. That's why the new frequency, I just removed the L in that equation and I replaced it with 2 over 3L. So this gives me this frequency here. So I've shown the fundamental frequency is equal to that. If the length is reduced to 2 over 3 of its current value, the velocity of the waves on the string is not changed and the new frequency will therefore be, so I will remove this. So the new frequency will therefore be V over 2, where there is L, I change it to the new length, which becomes 3 over 2. When I just reorganize this, it becomes 3 over 2 times V over 2L. And when I substitute, I get 441 Hertz. A particular string resonates in 4 loops. So I will sketch these loops 1, 2, 3, 4. This is 1, 2, 3, 1, 2, 3, 4. There are 4 loops at a frequency of 280 Hertz. So these are 4 loops and it is a string. So this is going to be F4 equals to, of course, 4 times F0. And they say the frequency here is 280. So this is 2 equals to 280 Hertz. Name at least 3 other frequencies. So I first find the fundamental. So here F0 is going to be 280 divided by 4, which I think this is 70. So F0 equals to 70. So in general for a string, we know that Fn is equal to n times F0, where n is equal to 1, 2, 3, 4, and so on and so forth. So I'll the first one is going to be 70. The second one is going to be 2 times 70. The third one is going to be 3 times 70, 4 times 70, and so on and so forth. So this gives us the frequencies as 70, 140, 210, 350, and so on and so forth. So those are the frequencies. The velocity of waves on a string is 92 meters per second. If the frequency of standing waves is 475 Hertz, how far apart are two adjacent nodes? Remember, the distance between a node and another node is always half of wavelength. It is half of wavelength. So all we need is to find the wavelength. The wavelength is going to be V over frequency from the general wave equation, where V is 92 over the frequency, which is 475. And this is the velocity of waves on a string is 92. If the frequency of a standing wave is 47, how far apart are two adjacent nodes? So the wavelength is going to be 92 over 475. So it means the distance between a node and another node is going to be a half of 92 over 475. So I'll have to divide this by 2, which gives us 0.097 meters. So that is 0.097 meters. You can always pause the video and try to see if you can calculate it. If two successive overtones of a vibrating string, it is a string. So if it is a string, if the first one is F1, the second one is F2, and so on and so forth. So they are successive, that means one to the next. So in general, remember for a vibrating string, the frequency Fn is equal to n times F naught. So if this is the first one, then the next one is going to be, we'll go on adding 1 because all harmonics are present. So the second one is going to be Fn plus 1, which will be n plus 1 times F naught. So what is the frequency of the fundamental? So I have just to combine these two equations. So I can say the change in frequency, or the difference in the fundamental frequency. Or if I subtract these two equations, I can just subtract these two equations. Let this be Fn, and let this be Fn plus 1. So I'll say 350 minus 280 is going to be equal to n times F naught minus n F naught is going to be, they cancel out. Then I remain with just F naught. So it means F naught is just going to be the difference between those two. I'm subtracting these two equations. Maybe a layman may not easily see this, especially the non-mathematicians, so I have to reorganize this. So if for the first mode of vibration, the frequency Fn is equal to n times F naught. For the second one is going to be Fn plus 1, which will be n plus 1 times F naught. So when the second one is Fn plus 1. When I open this bracket is n F naught plus F naught. When I open that bracket there, then I'm going to subtract Fn plus 1 minus Fn to be equal to n F naught plus F naught minus n F naught. I subtracted this equation minus this one here. So this one cancels out. But this one is 350 minus 280 equals to F naught. So this gives us F naught as being equal to 70 Hertz. So that is the fundamental frequency. Just so the fundamental frequency is going to be 70 Hertz. A string 75 centimeters long is fixed at one end. The other end is moved up and down with a frequency of 15 Hertz. The frequency gives a stationary wave pattern with 3 complete loops on the string. So there are 3 complete loops, 1, 2, 3. And this is a string. So this is going to be F3 equals 3 times F naught. The frequency is 15. So it means we now know the fundamental. So F naught is going to be 15 divided by 3, which is going to be 5 Hertz. The fundamental is 5 Hertz. The frequency gives a stationary wave pattern with 3 complete loops on the string. Calculate the speed of the progressive wave which have interfered to produce the stationary wave. So we now know the fundamental frequency as 5 Hertz. Then from the fundamental frequency being equal to V over 2L for a string. So it means F is 5 equals to V divided by 2 times L. 75 is the same as 0.75. So I'll say 2 times 0.75. So of course, when I make V the subject, V is going to simply be 7.5 meters per second. So a cell A string vibrates in its first normal mode with a frequency of 220. So we can take that to be the fundamental. Determine the frequency of vibration when the string vibrates in 3 segments. Those are 3 loops. In other words, so I want to find F3. So F0 is 220, and we want to find F3 because it's a string. We know that Fn is equal to n times F0, where n equals to 1, 2, 3 for a string. So it means for 3 segments, the frequency of vibration when the string vibrates in 3 segments will just be 3 times 220, which is 660. So I think that one is direct. So the frequency here is going to be 360 because there are 3 loops, 3 segments. So that is 360. You can also see that you can, if you want, you can rederive this as we did in lesson 9. Find the fundamental frequency and the first 2 overtones of an organ pipe, which is 0.17 meters long and closed at one end. So if it is closed at one end, we know that the fundamental mode, you can sketch this for simplicity. So we remember the length L was a quarter of a wavelength, which meant that F, which is V over lambda, F was equal to V divided by 4L. That was F for the fundamental. So the question is, find the fundamental frequency. We have the speed and we have the length. So the fundamental frequency is going to be the speed, which is 340 divided by 4 times the length of the pipe, which is 0.17. So this gives us 340 divided by 4 times 0.17. So this gives us the fundamental frequency is 500 Hertz. So find the fundamental frequency at the first 2 overtones. So the first 2 overtones. Remember, for the closed pipe, we only have odd harmonics. So Fn is equal to n times F0, but here n is only odd numbers. N is equal to 1, 3, 5, and so on and so forth. So it means the next one is going to be F3 because this one is going to be F1. F1 is equal to F0. So F3 is going to be equal to 3 times 500, which is going to be 3 times 500, which is going to be 1,500. Then the other one is going to be F, say the first 2 overtones of an organ pipe, which is enclosed at one end. So the next one is going to be F5, which is going to be 5 times 500, which is 2,500 Hertz. So those are supposed to be the values here. So this is supposed to be, I think, 500. A violin string with a fundamental frequency of 440 Hertz so what are the frequencies of its 2 overtones? So it is a string. If it is a string, we know that Fn equals to n times F0, where n is equal to 1, 2, 3, and so on and so forth. So you can just check these values. I will not check them. You can make an empty lemonade bottle resonate by blowing across the top. What fundamental frequency of vibration would you expect for a bottle 25 centimeters deep? The speed of sound in air is 340 meters per second. So you can think of an empty lemonade bottle as being a closed pipe. And you can find the fundamental frequency for a closed pipe, F. Fundamental frequency for a closed pipe is equal to V over 4 times L. So you can always sketch it to remain if you want to derive. Remember, L is equal to a quarter of a wavelength, which means the wavelength is going to be equal to 4 times L. So using F equals to speed over wavelength, the wavelength is 4L. I'll just press my calculator. You can do the working systematically. I'll just say 340 divided by 4 times 0.25. So I expect you to get here an answer such as 340 hertz. What fundamental frequency? I think it's 340. The speed of waves on a certain stretched string 48 meters per second is 48 meters per second. When the string is vibrated at a frequency of 64 hertz, stationary waves are set up. Find the separation of successive nodes in the stationary wave. So the speed is this, and when the string is vibrated at a frequency of 64 hertz, stationary waves are set up. Find the separation of the successive nodes in the stationary wave pattern. So all we need to find is the wavelength. So the wavelength is going to be equal to V over frequency, which will be equal to 48 divided by 64. So this is the wavelength in meters. So distance between a node and a node is equal to half of wavelength. So I'll say 48 divided by 64 times 2 in the denominator. So 48 divided by 64 times 2, which gives you a 0.375 meters, or approximately 3. If you multiply that by 100, that is approximately 37.5 centimeters. A certain organ pipe closed at one end can resonate at consecutive frequencies 640 Hz, 896 Hz, and 115 Hz. Deduce its fundamental frequency. So it is closed at one end, and these are consecutive. That means one to the next. So of course we know that for odd harmonics they differ by 2, because if the first one is F1 equals to F naught, the next one is F3 equals 3 times F naught, F5 equals to 5 times F naught. So it means in general, if the first one is Fn equals to n times F naught, the second one is going to be Fn plus 2. They differ by 2. So this will be n plus 2 times F naught. So I'm going to just make this one to be 640 being equal to n times F naught, and I use this one, which will be 896 being equal to n. I'm opening this bracket. That is n F naught plus twice F naught. So I have now these two equations, and I'm going to subtract them. So I have 896 minus 640 being equal to, when I subtract this and this cancels out, so I remain with the twice F naught. So it means F naught is going to be equal to 896 minus 640 divided by 2, which I think it gives us that. Or I could use another pair, but remember they just differ by 2. N differs by 2, since only odd numbers are available if the pipe is closed. Okay. So 13, determine the frequency of the first overtone of a sound note set up in a pipe of length 0.5 meters if it is open at both ends, and if it is closed at one end. Of course, if it is open at both ends, we consider it as being an open pipe, and if it is closed at one end, so we consider it as being a closed pipe. So do not forget, for an open pipe we have something like this. in the fundamental mode of vibration, where the length L is equal to a quarter plus a quarter, which gives us a half of wavelength. So determine the first frequency of the first overtone. Of course, the first overtone is a frequency higher than this. So for the first overtone of an open pipe, this was the fundamental. For the first overtone, I have to introduce a node. So this is what you have. So you have a quarter plus a half plus a quarter, which means L is representing a full wavelength. So the frequency here is going to be V over lambda, which is simply the same as V over L. So the length is 0.5. So for a closed pipe, therefore, the frequency is going to be the speed, which is 330, divided by 0.5, which is twice of 0.5, that is, twice of 360, which is 660 hertz. So this should be 660. Then for a closed pipe, still for the first overtone for a closed pipe, so one end must be closed. Remember the fundamental, we have only one node. So for the we have to introduce another node. So in the process of introducing another node, we have to introduce another antnode. Something like that. I think that is the first overtone. And this is a half plus a quarter cycle. So L is representing, those are 3 quarters, 3 over 4 lambda. So which means our frequency is equal to V over wavelength, which is, here the wavelength is going to be 4L over 3. So this will be V over, the 3 goes up, it becomes 3V over 4L. So the frequency becomes V, which is 330 times the 3 divided by 4 times L, which is 0.5. So this is going to be 495. So I want you to notice that the first overtone of an open pipe is higher, has a higher frequency than the first overtone of a closed pipe. Even, by the way, the fundamental frequency for an open pipe is always higher than that of the open pipe or the closed pipe. So it implies, therefore, that an open pipe will give a better quality of sound than a closed pipe. So in most cases, the quality of sound produced in an open pipe is better than that produced in a closed pipe. Okay, so I think these frequencies are obviously correct. And I said the quality of sound produced in an open pipe is always better than the quality of sound produced in a closed pipe. And that is very, very important for us to note every time. Okay. Determine the frequency of the first three. Determine the frequency of the first three harmonics of the culvert if it is a cylindrical in shape and open at both ends. So it is going to behave as if it is an open pipe. I take V to be 343 as the speed of sound in air. What are the 3 lowest natural frequencies of the culvert if it is blocked at one end? That is, now if it is converted into a closed pipe. For the culvert open at both ends, how many of the harmonics present fall within the normal human hearing range? Of course, we know this normal human hearing range. So since it is behaving as an open pipe first, in the fundamental mode, we have already seen that the frequency is equal to V over 2L because the length here is a half of a cycle. So it means the wavelength is twice L. So we have the speed V and we have determine the frequency of the first three. The first three, did I give the length here? Okay, so we're going to assume that the length of the culvert is 1.23 meters. So we just substitute in this equation. V is 343 over 2 times L, which is 1.23. That gives us the fundamental frequency, which from my calculator it is about 140 hertz to two significant figures. So what are the three lowest natural frequencies of the culvert if it is blocked at one end? So this is the fundamental. So this was the first frequency. This was the fundamental frequency. Then for the open end, we know that Fn equals to n times F naught, where n equals to 1, 2, 3, and so on and so forth. So if the first one is 140 hertz, the second one should be 140 times 2, which is 280 hertz. The third one will be 140 times 3, which is 420 hertz, and so on and so forth. So that will be for the open one. Then for the closed end, one end is blocked so that we have a closed pipe. Of course, we know that for a closed pipe, Fn equals to n times F naught, where n should be an odd number, but we need to find F naught. For a closed pipe, the fundamental F naught is equal to V over 4L, I think. Because for a closed pipe, remember, if we try to sketch it, L is equal to a quarter of a cycle, which means wavelength is equal to 4L. So if I use F equals to V over lambda, lambda is 4L. So the fundamental is V over 4L, which would be equal to 343 divided by 4 times the length, which is 4 times 1.23, then 343 divided by the answer. So this is approximately 70 hertz. That is to one significant figure, or you can write 69.7. So remember, for this one, n must be 1, 3, 5. For a closed pipe, we only have odd numbers. So if the first one is F, the frequencies for the first one is going to be 69.7. The other one is going to be times 3, around 209.1. Then the other one is times 5, 69.7 times 5, which gives us around 348.5, or approximately 350, and so on and so forth, since we wanted the first three. Then for the culvert open at both ends, how many of the harmonics present fall within the normal human hearing range? Okay, I think I'll solve this on the next slide. So here I think this is easy. This is easy for us to see how we get the fundamental frequency and how we use the fundamental frequency to get the other frequencies for the open pipe. I think that one is easy for us. Then if it is closed at one end, we saw the fundamental frequency as this. And remember here, when I use Fn equals to n times F naught, I've said n is only the odd numbers 1, 3, 5, and so on and so forth. So I can now use this to find the frequencies in that case. And the frequencies, I obtained them as the first one was, the fundamental was 69.7 hertz. So the second one is 209.1, then 348.5, and so on and so forth. So the question was for the culvert open at both ends, how many of the harmonics present fall within the normal human hearing range, which is 20 and 20 to 200. So because all harmonics are present for an open pipe, then we can simply express these harmonics as Fn equaling to n times F naught, because all of them are present. So the maximum, of course, is 20,000 for a normal human ear. So I will say 20,000 is equal to N times the fundamental, which was for an open pipe, I think it was 139 or 140. I'll just take 139. I had rounded off to two significant figures. So it means N is going to be equal to 20,000 divided by 139, which gives me 143 point something. So I round off the nearest to the smallest whole number. It is 0.88. So this becomes 143. I can't round off this to 144 because it means the next harmonic does not fall within. When I round off to the next one, it means I've forced another harmonic to fall within the range, yet the other one does not fall within the range. So it is, you round off to the smallest number, which is 143, even if it is 143.88. So the answer is going to be 143. But of course, only a few harmonics are of sufficient amplitude to be heard by the human ear. So because all harmonics are present for an open pipe at both ends, we can express the frequency of the highest harmonic heard as being Fn equals N F naught, where N is the number of harmonics. And if we try to find the number of harmonics, it is approximately 143. And of course, not all of these harmonics are heard by the human ear. Only a few of them have enough amplitude to be detected by the human ear. Okay. The overall length of a picole is 32 centimeters. The resonating air column vibrates as in a pipe open at both ends. Find the frequency of the lowest note. So the lowest note is going to be the fundamental. The lowest note that a picole can play, assuming that the speed of sound in air is 340. Opening holes in the side effectively shortens the length of the resonant column. If the highest note a picole can sound is 4,000 Hz, find the distance between the adjacent antinodes for this mode of vibration. So a picole is an open pipe on both sides. So it is an open pipe on both sides. So in the fundamental mode for an open pipe, we have an antinode here and an antinode here. So remember, the distance between two adjacent antinodes is equal to half of wavelength. So we can first of all find the wavelength here. So the wavelength is going to be the length of the pipe, which is 32. 32, I think it is 0.32, then times 2, which gives us a 0.64 meters. So that is the wavelength. So if I want to find a frequency here, so the frequency is going to be V divided by the wavelength, which will be 340 divided by the wavelength, which is 0.64. And I think this gives us 340 divided by 0.64. This is around 530 Hertz to two significant figures. Opening holes in the side effect shortens the length of the resonant column. If the highest note a picole can sound is 4,000 Hertz, so the frequency is 4,000, find the distance between adjacent antinodes. So I'll first find the wavelength. So the wavelength is going to be V over the frequency. The V has remained 340. The frequency is 4,000. So this gives us the wavelength. 340 divided by 4,000. This is 0.085. Then the distance between adjacent antinodes is always half of wavelength. So I will just divide this by 2. So divide by 2. So this gives us 0.0425, or it is 40. When I multiply this by 100, it is 4.25 centimeters. Okay, I think that one is not very hard, as long as you know that a picole is like an open pipe, so that one becomes easy. So this was, I think we got this frequency. Then in part B, we got the distance as being 42.5 millimeters or 4.25 centimeters or 0.0425 meters. Calculate the length of a pipe that has a fundamental frequency of 240 Hz if the pipe is closed at one end. I've done an example like this one. I'll just press my calculator and it is open. Of course, for an open pipe, we know that, for the first part is closed. So Fn equals to N times F naught, where N is equal to 1, 3, 5. But they want the fundamental frequency. The fundamental frequency for a closed pipe is equal to V over 4L. The fundamental frequency for an open pipe is equal to V over 2L. From these expressions, since I know calculate the length of a pipe that has a fundamental frequency of 240 if it is closed. I know F naught, the speed is 340, so I can find L. And if it is open, so you just substitute and find those lengths. This is very easy. I will not solve this. I even solved it here. I was always saying that you can always sketch in case you don't really remember what happens. If a closed pipe, you have in its fundamental mode, you have a quarter a cycle. So the length L is equal to a quarter of a cycle, which means the wavelength is 4L. And F, remember, is V over lambda, where lambda is 4L. For an open pipe, remember, both sides are open. So we have an antnode here and an antnode the other side, something like that. So this is a quarter plus a quarter, so the length represents a half of a cycle, which means lambda is equal to twice L. And then remember F equals to V over lambda, which lambda is 2L. That's how we come up with these answers here. The fundamental frequency of an open organ pipe corresponds to middle C, which is 261.6 Hz on the chromatic musical scale. The third resonance of a closed organ pipe has the same frequency. So the other one is an open pipe. This one is a closed organ pipe, has the same frequency. What are the lengths of the two pipes? What are the lengths of the two pipes? Okay, so I will sketch this. So for an open pipe in its fundamental mode, this is what we have. We have an antnode here, we have a node and an antnode. So we have something like this. So it is antnode, node, and antnode. So we can find the length here. So we know that wavelength is equal to speed over frequency, which is going to be 340 divided by the frequency, which is 261.6. And this gives us 340 divided by that. So this gives us a 1.31 meters. So remember this here, this is a quarter plus a quarter. So here the length is a quarter plus a quarter, which is half of wavelength. So for the first one, for the open pipe, L is going to be equal to a half of wavelength, which means the length is going to be 1.31 divided by 2. So for the open pipe, the length is going to be 1.31 divided by 2. The length is going to be 0.656 meters. Then the third resonance of the closed organ has the same frequency. So if it is a closed organ pipe and it is the third resonance, remember for the first resonance we had something, for the first resonance we have something like this. For the second resonance, For the second resonance, we introduce another node. So if I introduce a node, I would have something like this. For the second resonance, we have something like that, where we have one node there. For the third resonance, I have to introduce another node. So we have one node, we shall have to introduce another node. So I'll have something like this. So I have 1, 2, 3 nodes. That is for the third resonance. I have 3 nodes. So for the third resonance, I want you to notice that the length L is equal to a quarter plus a half, which means 5/4 of wavelength. So for a closed pipe, the length L is equal to 5/4 of the wavelength. And since our wavelength is 1.31, so it means L is going to be 5 divided by 4 times 1.31, which gives us 5 times 1.31 divided by 4. So this is 1.64 meters. So for the closed pipe, it is going to be 1.64 meters if it is the same frequency. Because if it is the same frequency for the same speed, it is going to be the same wavelength. So that's why I used 1.3. Okay, so I think I solved this in details. We got the wavelength, and I explained that the length of the open pipe vibrating in its simplest mode is antinode, node, antinode. That is what I made here. I've sketched. Then for the closed pipe, we have node to antinode for the first mode of vibration, node, antinode for the second mode of vibration, which I sketched in green. Then we have node, antinode, node, antinode, node, antinode in red. So this gives us 1, 2, 1, 2, 3 for the third. So that gives us that pattern. So that is 5/3. I mean 5/4 of wavelength. That's how we came up with L as being equal to 1.64 meters. When an open metal pipe is cut into pieces, the lowest resonance frequency for air column in one pipe is 256 Hz, and that for the other is 440 Hz. How long was the original pipe? How long was the original pipe? And part 2, what resonant frequency would have been produced by the original length of the pipe? V is 340. So suppose 240 Hz and 440 Hz are the lowest resonances of the enclosed air columns, and if they are consecutive, then we can find for the first one. For the first one, if I use 256, let me use this space, 256. If I use 256 Hertz, so the wavelength lambda is going to be equal to V over the speed, over the frequency. The V is 343 divided by the frequency, which is 256. So this gives us a wavelength of the first wavelength is going to be 1.34 meters. What is the length of the pipe therefore? Remember, this is an open metal pipe is cut into pieces. The lowest resonance frequency for the column in one piece is that. So remember, this is an open pipe now. If it's an open pipe, in its fundamental mode, L, we have an antinode here and an antinode there and a node between. So L is equal to the distance between the antinode and antinode, which is half wavelength. So L is equal to half wavelength. So it means L is going to be half wavelength, which is going to be 1.34 divided by 2, which is 0.67 meters. If I try to consider a frequency of 440 as the next, remember for an open pipe. So I will have that 400 and I will have that the wavelength lambda is going to be equal to V over frequency, which is going to be 343 divided by 440, which will be equal to, from my calculator, I get 0.78 meters, which means the length, which is the distance between an antinode and antinode, the distance between an antinode and an antinode is going to be equal to 0.78 divided by 2, because the lowest resonance frequency of the air column in one piece is this, and that in the other. So in the other piece is going to be 0.78 divided by 2, which is, I think, 0.39 meters. So how long was the original pipe? So if there are two pieces, we get this one and add it to the other one. So I'll just add 0.39. So total length is going to be 0.67 plus 0.39, which gives us, I think this is 1.06 meters. That will be the total length of the pipe. What resonant frequency would have been produced by the original length of the pipe? So the original length of the pipe. So now it means I have now to find a new wavelength in this case, because if L equals 1.06, and remember the distance between an antinode and an antinode is going to be equal to half of wavelength. And in the fundamental mode of vibration, if L is 1.06, then it means we shall say that 1.06 is equal to a half lambda, which means that the wavelength is going to be 2 times 1.06, which gives us 2.12 meters. So if it was one pipe of length 1.06, the wavelength in the fundamental mode is going to be 2.12 meters. Then if I try to find the frequency from V, which is 340, divided by the wavelength, which is 2.12, what does this give us? So this gives me 1.61, not no 161.8. So that would be the frequency if it was used as one pipe of length 1.06. That would be its fundamental frequency, or the lowest frequency. Okay, so you notice that if the pipe was used as a longer pipe, the lowest frequency is smaller than when it is used as a shorter pipe. So shorter pipes produce waves or sounds of higher frequency than longer pipes in that case. So suppose these are the lowest of the enclosed air columns. So I found the frequencies, I found the wavelength of each, and then I found the length of the pipe of each in the fundamental mode. Then for the second one, I also found the wavelength of each wavelength, and I found the length. So the original length was the sum of the two, which is 1.06. Then if it is used as a whole in part B, it is used as 1 in part B, the distance between an antinode and antinode is half wavelength. And remember, the distance is going to be 1.06 if it is used as a whole length. So that means the wavelength is twice. When I find the frequency, that gives me 161.8 hertz. What will be the fundamental frequency and the first three overtones for a 26 centimeter long organ pipe at 20 degrees Celsius if A, it is open and B, it is closed? The speed is 340 meters per second. Of course, the temperature here will not be useful. So I've done a similar question. Like this one. I don't think I need to go through it any further. So this one I've already solved a similar question. Open pipe, its fundamental mode, you can sketch it in case you don't remember the formula for the frequency. You know this is a quarter cycle, so the length is equal to half a cycle, which means lambda is equal to twice L, and frequency is V over lambda, which will be V over 2L. So that gives you the fundamental frequency. So you can now find other frequencies from Fn equals to N F naught, N times F naught, where N is 1, 2, 3, 4, a closed pipe. For an open pipe. Then for a closed pipe, you can sketch the fundamental mode of vibration, where you have only one node and one antinode. So this is a quarter of a cycle. So L represents a quarter of a wavelength. So wavelength is 4 times L. Remember, F will therefore be V over 4L. So you can get the fundamental. And then for a closed pipe, remember, only odd harmonics are present. So Fn is equal to Nf naught, where N is only an odd number. So you just substitute and get the corresponding frequencies. I think I've done so many examples. Let me just do one more example. An organ pipe has two successive harmonics. They are successive. That means one to the next, with the frequencies 1372, 1764. Show that this is a stopped or closed pipe. What two harmonics are these? And what is the length of the pipe? So if it is a closed pipe, the values of N are going to be only odd numbers. Remember, for closed pipes, N differs by 2. If the first one is Fn equaling to N times F naught for a closed pipe, the next one is going to be Fn plus 2 equaling to N plus 2 times F naught. So I'll call this one Fn, and I'll call this one Fn plus 2. So I'm trying to find the fundamental of this. So I'm going to just subtract. So I'll say Fn plus 2 minus Fn is equal to N plus 2 into brackets F naught minus N F naught. So I have 1764 minus 1372 being equal to F naught minus F naught disappears, so I'll remain with twice F naught. So what is F naught? I'll subtract and divide by 2. So it is 1764 13 1764 minus 1372 divided by 2. So F naught is going to be 196 hertz. That is the fundamental. The question is, show that this is a stopped or a closed pipe. So the fundamental is 196 hertz. So let's try to check the values of N using the first one. What is the value of N for the first one? So Fn equals to N times F naught, which means N is going to be Fn, which is 1372 divided by the fundamental, which is 196. This gives me N as being equal to 7, which is an odd number. Let me check the next one. Fn plus 2. So we have again N equals to 1764 divided by 196. And this is giving me N as 9. So it means the harmonics are going to be the 7th and the 9th. These are odd numbers. The eighth has been skipped, so this is enough to prove that it is a closed pipe. So what two harmonics are these? We have said the seventh and the ninth. And what is the length of the pipe? What is the length of this pipe? So for a closed pipe, remember, for the fundamental mode of vibration, F naught is equal to V over 4L for the fundamental mode of vibration. So it means I can find L easily. So L is going to be equal to V, which is, let's say V was not given here. Okay, I will assume V is 340 divided by 4 times F naught, which is 196. Of course, V should be 340, approximately 340 or 343, the speed of sound. And I think this gives us the length. So this is 0.43 in meters. Okay. So I've got I tried to verify that is closed. I got the first equation, the second equation, because successive harmonics in a closed pipe differ by 2, n differs by 2. So when I combine these, I was able to find the fundamental frequency, which was 196. Then I back substituted and I got n for the first frequency as 7. So I've also checked n for the second one to be 9. Okay, so the pipe is stopped because the solution gives the odd integer number n equals to 7, as it should be an odd number. And these are the seventh and the ninth. You can check that for the second one, n was 9. And for a closed pipe, I've already shown that L is equal to V over 4 F naught, which gives us that, assuming that the speed of light, the speed of sound in air is 340 meters per second. Okay, so I think this should be the end of lesson 2, lesson 10. Lesson 11, we shall talk about diffraction alone. Until next time, bye bye.